Hey everyone, this is Mohammed Nadeem and welcome to my YouTube channel. Today in this lecture, we will discuss about the motion of the charged particles in external magnetic field. As we discussed in the previous videos about the force and the current carrying conductors, and we will generalize that into the force and the single charge particle when we move that single charge particle in external magnetic field. We have the atom. Okay, in atom we have the nucleus which is present at the center having positive charge, and the negative charge electron is moving around this positive charge in shell. Okay, and we know that this electron will be present in the orbital, and inside the orbital we have electrons, and that electrons is in the spin. Okay, due to that spinning it will produce the magnetic field. Okay, and inside the orbital we have two electrons. When let's say here this is moving anti-clockwise direction. Okay, the other one will be moving in clockwise direction, and due to its motion, due to its spinning, it will produce the magnetic field. So here in this case it is moving in anti-clockwise direction. The upper side of this electron will be the south, and the lower side of this electron will be the north. Similarly, we have that same electron in the same orbital but in opposite spin. Due to its opposite direction, now this side will be the north and this side will be the south. So here in this case, this side was the south, and now it become the north due to the change in the direction of the spinning of the electron in the same orbital. Okay, so here in this conductor, let's say we have these metal atoms. Let's say this is the copper atom, and the copper atom have more electrons, and their outermost electron is present far away from the nucleus. Therefore it can be free even at room temperature, and that we call a free electrons. Okay, so these are large number of free electrons as indicated by the blue color here. Okay, these are the free electrons. Now, when the external battery, okay, the potential difference is not provided to this conductor, these electrons are moving randomly. This electron moving in this direction, okay, this electron moving in this direction, this electron moving in this direction, this electron moving in this direction, and overall effect is zero. The drift velocity, the net drift velocity of this conductor is zero. And if we provide the external battery, due to which the potential difference will be created and the electric field will develop inside the conductor, and due to which the force on each the free electrons will be exerted, and due to which each electron will be aligned in a specific direction due to external battery. Okay, mean that these free electrons will now move in the same directions. Okay, so its net velocity is not zero. And as we know here from here, that when the charge is in motion, it will produce the magnetic field. So here these charges are in motion. These free electrons being negative charges are in motion. So when these free electrons are in motion, it will produce the magnetic field around itself. So here this electron will produce the magnetic field. Similarly, this electron will produce the magnetic field. Similarly, this electron will produce the magnetic field. And inside this conductor, we have large number of free electrons. All are moving in the same direction. Therefore, each electron will produce the magnetic field. So if we add that all magnetic field from each electrons around this conductor, there will be the magnetic field. If we place this conductor here, so this is the conductor. If we provide the external source to this conductor, the free electron will move in this conductor. Okay, so due to the motion of the free electron around this conductor, there will be magnetic field. Conductor is behave like a magnet, and similarly the external we have magnet. So there will be the force of interaction between this magnet, and due to which this conductor will be moved inside the external magnetic field. Now the magnitude of the force on this conductor due to the interaction of its own magnetic field with the external magnetic field is given by these parameters. So here, the force and this conductor depend upon this external magnetic field. So here we have the external magnetic field, and the direction is from this north toward this south. It means that if we increase this external magnetic field, then more force will be exerted on this conductor. Okay. So here we conclude that the force in this case, force is directly proportional to the external magnetic field. Okay, and similarly, the second one here, that if we increase the current in this conductor, okay, so due to that current, so if we increase the current, then more magnetic field will produce around this conductor. Okay, then more magnetic field will produce around this conductor, and due to which the much more interaction will be occurred with the external magnetic field. The force on this conductor depend upon the current in this conductor. So here this force is also depend upon the current in this conductor. And similarly, here the length of the conductor also depend and the force. So if we increase this length, which is present inside this external magnetic field, then the more force will exert on this conductor. So here the force on that conductor which is present in external magnetic field is also depend upon the length, and which is directly related. If we increase the length which is present inside the external magnetic field, then the force will also increase. So here we have to combine all these, and it implies that F is directly proportional to B, okay, the magnetic induction, the current in the conductor which is present in external magnetic field, and the length of the conductor. So here F is equal to, okay, equal and constant. So instead of this proportionality, we put this equal and constant, and this B, I, and L come in its own position. This constant is K, okay? K and its value is equal to 1. So it become F is equal to force is equal to mm, this is become 1. So this become the magnetic induction, the current, and the L. So this is the formula for the force exert on this conductor. Okay, the force exert on this conductor due to the interaction of its own magnetic field with the external magnetic field. So we have this formula. Let's call this as equation 1. Now we are going to generalize this equation toward a single particle. Okay, so here we consider large number of particles, large number of free electrons, and we call that as a conductor, and we put that inside the external magnetic field. And now we are going to put only a single free electron inside the magnetic field. So for that, we are going to generalize this equation. So here in this equation, we have I is actually the current, and current in this conductor. Okay, so here current in this conductor, and we know that the for equation for the current is given by this I is equal to, okay, the number of the charges, okay, passing through the area per time. So this is called the current, and here we have the number of the positive negative free electrons passing through in this conductor. We call them as this is a current. So here this current is due to the number of these free electrons. So for that I am putting in, so I is equal to NQ by T. Okay, So, due to the external battery, the source of EMF, the electric field will develop inside this conductor, and due to which the force will exert on this conductor, and due to which these free electrons, these free electrons will be move. Okay. Will be moving. So that motion of these free electron we call as a drift velocity. Okay, so here we have drift velocity, and we know that v is equal to v is equal to uh, velocity is actually we have the length divided by time. So in here we are going to find the relation for this L. Okay, length. So for that this L will become equal to this L will be equal to V T. So let's say we call this as equation 2 and we call this as equation 3. So put the value of I from this equation 2 and here the value of L from this equation 3. So this equation will 1 will become this. So here we have equation 1 now implies that if okay the force which is equal to this magnetic induction, and instead of this I will put in q by t. Okay, and instead of this L I will put this equation which is equal to uh, v and t. So here this t and this t will be cancel each other, and this equation become this. So this F okay is equal to B the magnetic induction, and this N and this Q and this V. So this is actually the force and the number of the charges moving in this conductor. So the force and the number of the free electrons moving with velocity, a drift velocity of v in and when we put that in external magnetic field. So here this is for n number of free electron, and so if we put the n is equal to 1 here in this above equation, then this equation will become this. So here this equation will be F is equal to B, and this n become 1. So here this become Q and this is V. So this is the force. This is the force and the single free electron when we put that single free electron in the external magnetic field. So here we have that same scenario as we discussed that if we move the charge in the external magnetic field. So let's say we have the charge. Okay, we have the charge, and we move that in the external magnetic field. Okay, and that charge is moving with velocity v. Okay, we have this charge as a free electron, a single free electron that is moving with velocity v in external magnetic field. Then there will be the force exert on that. I am going to start this. So here this charge is now this the force exert on this charge, and due to which it change its own path. Okay, so here again see here that if the free electron, okay, so if this electron is moving, okay, then the force will exert on that when it enter the magnetic field. So here this equation becomes satisfied that the force F will be exerted on the charge when that charge is moving with velocity in the external magnetic field. So this is that force. And the direction of this force is determined by this right hand rule. So here we have the thumb represent the motion of the charged particle, and this straight fingers represent the motion. This straight finger represent the direction of magnetic field. So here in this case, the direction of magnetic field is towards you from your screen, and the force will exert Okay, the palm of your hand, right hand, uh, perpendicular to your palm, this will be the force and the free charge. So this free electron. Okay, so from this right hand rule, we determine the direction of the force exert and the free electron when we move that free electron in the external magnetic field. So, as we saw in the previous simulation, that when the charge particle move inside the external magnetic field, it will follow the circular motion, and that circular motion is due to the force exert and that due to the force exert and that free electron. So here the circular motion, okay, if centrifugal force, the force in the circular motion is given by the centripetal force, which is equal to mv square by r, and this centrifugal force and the charged particle in the external magnetic field is due to the force and it is due to that magnetic force, and which is given by this, okay, which is given by this. Okay, so here we have that f of b, which is equal to q, v, and b. So this if B is responsible for this centripetal force, so this equation and this equation are same. So this is the source for the centripetal force. Therefore, we can write this as this is the m v square by r is equal to q v and v. So here this v and this v square will be cut, so it will become mv by r and q and b. Okay, this is the magnetic induction. Okay, so from here we know that here this particle will now move in the circular form. Okay, so here now the velocity is become the angular velocity. So for that we can put here as angular velocity. So v is equal to r omega is the angular velocity. So here this become m. Okay, and instead of this we will put r omega and divided by the r, which is equal to the q and the magnetic induction. So this equation now become this r and this r will be cancelled, and here we have this m and this is the omega, which is equal to the q, and this is the magnetic induction. Okay, so from here this omega is given by q b magnetic induction divided by m. Okay, so now the free electron is moving in the circular path, so and there will be some time period for that motion. So the time period for that angular motion is given by t is equal to 2 pi by omega, and here this is equal to 2 pi divided by omega, and the value of omega is this, so which is equal to q b divided by m. This is the value of omega. So here it will become equal to t is equal to, okay, this 2 pi, and this m will be multiplied with that and divided by q, and this is the magnetic induction. So this is the relation for the time period of the motion of the free electron in the external magnetic field. Now the frequency for that is given by F is equal to 1 over time period, and it become 1 divided by this equation, which is 2 pi m divided by q, and this is the magnetic induction. Okay, and this now become F is equal to q, and this is the magnetic induction divided by 2 pi m, and this is the relation for the frequency of the motion of the free electron in the external magnetic field, and we call this as a cyclotron frequency. Cyclo cyclotron frequency. So here we start from the magnetic field around the current carrying conductor, and then we place that inside the magnetic field. The force will exert on that conductor. Okay, and the force is due to the contribution of the magnetic field of the individual free electron moving inside the conductor. Okay, now we generalize that force due to these individual free electrons into a single free electron, and if we put a single free electron inside this external magnetic field, then there will be the force exert on this. So this first force is for the force and the current carrying conductor, which contain large number of the free electrons, and up to here we have that equation. And now we generalize that equation towards the force on a single free electron when we place that free electron, and that free electron is moving with velocity v, and when we place that moving free electron in external magnetic field, then this force will exert. Okay, and we saw in the simulation that this force is exert on this moving electron in the circular form. So here the concept of the centrifugal force come into picture. So from this so from here we have this force, and this is responsible for the centripetal force. So here I equalize these two equations. So from here we find the omega. Okay, and from that we find the time period. So if the free electron is moving inside the external magnetic field, there will be some time period. So because that charge is moving in the circular form, okay, and it will have some time period, and it is given by this. And so here that free electron will have some frequency as well. So that frequency is equal to 1 over time period, and which is given by this. So this is actually the frequency of the free electrons which is moving in circular path inside the external magnetic field.